This is part 2 of 10.5. As we learned all the new formula to find the area and an area between polar curves in polar coordinate system. Now we're going to look at the arc length in polar form. So let's recall the arc length in parametric form. So if you look at this one down here, this one, this formula here, this is the parametric form when we want to find the length of the parametric equations, right? So recall when you find the parametric equations where you have x equal y equal and something, let's say 3 t. We often use t or theta. So I'll say 3 theta plus 2, and then maybe 30 to the square minus 5, right? So we're going to find the arc length where you're given the interval of theta. Then we're going to use this formula, the integral from 0 to 3. You take a derivative of x and take a derivative of y, plug in, then do that, right? So that's in 10.3. Now we are in polar equations this time. Okay, so polar equations. Now if we're given polar equations, right? So in polar equations, we have r in terms of theta, so r equal say 2 sine of theta, right? Then how we're going to find the arc length when given, let's say from 0 to pi half. Now, don't forget that from polar equations, we can always convert to parametric equations using the two important formula, x is r cosine, y equal r times sine. For example, if r is 2 sine theta, I can turn that into the polar equations, x equal r, right? R is 2 sine, so it's 2 sine of theta times cosine of theta. And then the y equal r again is 2 sine of theta times sine of theta. And then we can use this formula. Take the derivative of x, derivative of y, and then we can go from there. Now, however, when we do that, you can see that we often end up with using the product rule for both x and y. So it's not so convenient. So instead, we want to develop another form or variations of this by doing it directly. Okay, so if you think about this, if x is r cosine, y equal r sine, I'm not going to do this in particular example like this. Instead, we're going to look at, say, x is r cosine, y is r sine. We can go ahead and do this in general. Okay, so by that I mean, let's say x is r cosine and y is r sine. Okay, and then when you apply this formula, then you're gonna see a derivative of dx d theta, right? So if x is r cosine of theta, then dx d theta. So again, it's product rule. You take a derivative of r times cosine, and then plus derivative cosine, well, that's negative sine. So negative sine theta times r. And then when r is and y is r sine of theta, then what's dy d theta? Well, derivative first times the sine plus derivative second, and derivative sine, we got cosine of theta times r. Then you're gonna plug this whole thing in here, right? So when you have R equal, L equal, and then alpha beta square root of big, right? So you're gonna square this plus to square that. Now, perhaps I just don't want to write a square root yet. Now let's square the derivative x and derivative y and try to simplify what's inside without the square root first, right? So if you square the x, the theta, right, you square that one, then you're gonna have the whole thing square. I'm gonna skip the detail. When you FOIL, you actually have r prime cosine of theta, that square plus 2 times this. So basically, you have 2. Let's square the second part, this one first. So then you're gonna square of negative sine theta times r, and then plus 2 times this is a minus, so 2 times this quantity times that quantity to be r prime times r times cosine theta times sine theta, right? So again, that's after you FOIL, and the same thing I do with the dy d theta square. Then you should have this r prime sine of theta square plus, again, this quantity square is cosine of theta times r squared plus 2 times this times this should be r prime r sine and cosine, right? Sine and cosine. Now, notice that when you square each, and then you're gonna add them up, right? So you're gonna have add up on both equations, so that'll give you the radicand inside. Now, the nice thing about this is if you're looking at the negative 2 r prime r cosine sine, these two actually the same opposite side cancel each other out. And then you're left with a whole bunch of square. But the nice things about that again is because of the trig identity could be used. You see, look at these. This r prime square, r prime square, right? So that is a derivative of r. Okay, so that's the derivative of r squared. And times cosine square, that's r prime square times sine square. When you factor out the r prime square, you should have cosine square theta plus sine square theta is there. Likewise, you see this has r square in common. Then if you take the r square out, then you should left with then sine square plus cosine square. And cosine square plus sine square, so that is 1. That is 1. So you see that we really end up with r prime derivative r square. I can change it to a more formal notation that the derivative of r with respect to theta square, and then that's r squared. So after all, what you simplify inside is just the derivative of r squared plus the r squared inside, you see here. All right, so that's how we get the new variations, the versions of this formula. And that makes things a lot easier when it's come to integrate or set up, right? So look at the example here. Find the length of the curve r equal 8 over theta on the interval from 1 to 3. Okay, so again, all the setup is what it's very straightforward, right? So the arc length will be the integral from 1 to 3. It's square root of r squared, right? So r is 8 over theta square plus the next part is the derivative of r squared. So you see from here, all you need to do is looking at what's the derivative of r here. Well, if you rewrite that, r is 8 times theta to the negative 1 power, right? Then the derivative of r here is just negative 8 theta to the negative 2, or negative 8 over theta squared. So you have negative 8 over theta squared. All right. And then if you want to clean up, just from 1 to 3, square root of, that is 64 over theta squared plus have 64 over theta to the 4th theta. All right. So I don't think we could do it by hands, but I'll clean up a little bit one more step here. Notice that here we have 64 over theta squared common. So if you take out 64 over theta squared common, that left with 1 plus, and that left with 1 over theta squared d theta. So when we do that, it's help at least clean up because this is the perfect square, right? So that's from 1 to 3. So root 64 is 8 of theta squared theta. So you have 8 over theta square root of, actually we could add, yeah, I think we could do better than that, right? So if you add the two together, it's theta squared over theta squared. So we actually have theta squared plus 1 over theta squared. Okay, so that's the under the radical. And square root of theta squared becomes a theta. So you're going to do one extra step here. So it's really 8 over theta squared. And then square root of theta squared plus 1. That is look much neat, right? Much more neat than the original. Now from here, you probably can see if we're going to integrate this by hand, then the thing that comes into my mind is the square root of something square here, right? But that is when we have to use what the trig sub members. So you're going to let theta be some angles, right? Either a sine or a tangent or a secant. Now, one thing is actually hard for this one, if we try to do it using trig sub, is we often let this variable be sine, tangent, or theta. But that one's already theta, and so that's been confusing. So one way you could do is you just change the name. So by that I mean it's really the same if you change all the theta back to the x. So the x squared over, right, 8 of x squared and then x squared plus 1 dx, right? So that's pretty much the same. And then from here you determine using the trig sub method, then let x be what functions. Actually, you can see this is tangent squared plus 1. We have the formula. So x should be tangents of theta plus 1. Let you finish from here. Otherwise, in most problems, when we're dealing with the arc length, the setup end up with the square roots of something inside. We like to use calculator or integration by table to finish that. Rarely can we do this by hand, but this one we probably could. As you can see, x equal tangent of not plus 1, but there's tangents, and that worked out very nicely, right? Now, the final formula that we would need is the surface area. Surface area. recall the surface area in general is 2 pi radius times the length, the arc length. Since we have the arc length formula, look at arc length formula. If you want to find the surface area, all you need is to multiply this by 2 pi the radius. So if we rotate about the x-axis, then notice that your radius here will be the y-coordinate of this point. And so that's why you have 2 pi y. That since it's in terms of theta, you're going to replace the y with r times sine, right? Y is r times sine. Similarly, when you rotate it about the y-axis, okay, so when the y-axis, you rotate about the y-axis, then your radius r here will be the x-coordinate of the point, so 2 pi x, but x is r cosine. Okay, right, so we have two formula, and then from here I can find the surface area. Okay, by using this two formula. And let's look at this example here. Find the area of the surface obtained by rotating the curve r equal 8 over theta on the interval from 1 to 3 about the x-axis. You see the example here, pick, it's pretty much like that one, right? So it's really the same curve. Instead of in previous example, 1 to 3, you're looking at, say, this curve right here, what's the length. Now, we are looking at the rotations about an x-axis. Let's say that's your x-axis, and you rotate, you're gonna get something. Again, I just make up the graph. It might not look like that, but you can get an idea from here. You rotate, that you have a surface, and we're gonna find the area of that surface. So the setup again will be exactly the same as above, except you will need to attach or multiply by 2 pi radius. Simply rotate about the x-axis, the radius will be 2 pi y, or 2 pi r sine theta. So the setup for the surface area is 2 pi, the integral from 0 to 1. No, sorry, from 1 to 3. 0, 1, 0, 1 to 3. Okay, from 1 to 3, r sine theta. Okay, so the r, okay, so I'm going to write here first as r sine theta, right? And then square root. And then you get the r square is 8 over theta square plus, and then you have negative 8 over theta square the theta. Remember, the derivative r is negative 8 over theta square, which is that one we have up here. Okay, now since we do all the work, now, it's pretty easy when it comes to simplify, right? Because what we know is this, after you simplify, it just become what? Let me see what we got up here. 8 over theta squared times the square root. All right, so it'll be 8 over theta squared times square root of theta squared plus 1 d theta. Then again, the r is 8 over theta times sine of theta. All right, so I think here's the setup. Again, it's pretty hard to integrate now, adding an extra sine of theta. So it will be used, we're going to use calculator to approximate the answer, and that will give us the area of the surface. Okay. So here's one other example. I'll do it quickly, and we have to use the graphing calculator to find the arc length and calculate to find the area of the surface. Okay. So that is the one again with the we find the arc length of one paddle, right? So one paddle, I think, well, you have to grab it just to see it, but I think it's either looking that way or something. It's gonna be four paddle, and it's in at the pole. So the first thing you need to find the theta at the beginning, I mean the initial or the beginning of the ends of um, the loop where's the theta run. Okay, so since its beginning ends at the pole, so this is where we set the r equals 0 and solve for theta. Okay, so we have cosine of 2 theta is 0. So therefore, 2 theta is going to be cosine of pi half or cosine of 3 pi over 2, right? So cosine of pi half is 0 and 3 pi over 2. 5 pi over 2, we could actually go on and on. But then we only pick 2, divided by 2, you have pi 4 and 3 pi over 4. Okay. So that is where you're going to have the first loop or one paddle. This time you find it, the one paddle. And so your arc length will be the integral from pi 4 to 3 pi over 4 square root of r squared. Again, r is this. So we have cosine of 2 theta squared plus, and then we need to find the derivative of r, right? So the derivative of r is negative sine of 2 theta times 2. So we have negative 2 sine of 2 theta, right? So that's the setup. And I might write one more step, if you will. It will be right, so that's really cosine squared 2 theta, and that is 4 sine squared 2 theta. You don't need to know this step. Basically, you can use calculator, approximate the answers. Done. Now for number 2, we're going to find the area of the surface, right, of this on this interval from 0 to pi 6. It's going to be the same as that one, right? Remember the surface area. This time, you're going to have a 2 pi radius. If we rotate about the y-axis, the radius will be x, and x is arc cosine of theta. Right, so be square root of, same as that one, cosine square of 2 theta plus 4 sine square of 2 theta. D theta. Right, so at the end, we need to do one more step. Oh, actually, forgot that from 0 to pi 6, right, because that's one it says there. So 2 pi 0 to pi 6 R again is cosine 2 theta. Cosine 2 theta times cosine theta, square root of cosine square 2 theta, the parentheses, plus 4 sine square 2 theta, d theta. All right, so that's all. And again, use calculator to approximate the answer. That finished the last sections of chapter 10.